Many problems within this section of our course describe the motion of an object, but they only look at a specific part of the motion. They don't look at a situation where maybe a car speeds up as it leaves a stop sign and then coasts at a constant speed and then perhaps slows down again. That sort of complicated motion, multi-stage motion, cannot be all put into a single equation. And so we're going to take a look at how to organize some information, how to build some strategies for dealing with situations where multi-stage motion is involved, where the acceleration of the object changes during different parts of its motion. Let's begin by looking at this from a graphical point of view. If I was going to talk about the situation that I just described, where an object, a car, accelerates away from a stop sign and then begins to coast at a constant speed, the acceleration would be constant for a while, and then it would drop to a different constant value, specifically 0. But in reality, a realistic situation, it would take time for that change to occur. It would be a gradual time. When we think about these from an ideal point of view in our physics class, we will talk about instantaneous changes in motion. And what that means is that if the acceleration was at this value to begin with, and then later it was 0 because we decreased the pressure of our foot on the accelerator, it's going to happen in an instant. So there is a vertical drop on the graph to the 0 acceleration. And so it's important to recognize that, because that means we cannot have a single function that somehow describes the motion. It's not a continuous description, and so it can't be a continuous function. So when you see a discontinuous graph like this, expect to have one set of information for this part of the motion and then one part for this part of the motion. Now, the velocity as well, in this case, we would have a positive slope, and then at some point it would begin to decrease and then eventually level off. Again, that's a realistic situation. This part of the motion takes time. But when we think about this in our problems, our velocity graphs will just look like this. At that change in acceleration point, it just suddenly becomes 0. All right, so again, this is not a realistic graph. You can't write a function, unless it's a piecewise function, for this sort of a graph. But we do want to notice how this point here, the ending value of v for our line, does exactly match the constant value of v for the rest of the time. And so even though the position graph is harder to see, I'm not really going to draw both of them here, we would imagine that the slope here would get greater and greater and greater, and then at this moment where the acceleration changes to 0, at that moment then my position graph should continue on with a perfectly straight line. Okay, so again, that gets at the idea that my value of velocity is going to be the same at the end of the first stage versus the beginning of the next stage. And then here, that the slope of my graph at the end of the curve section should match the slope of the straight line section. All right, let's take a look at just some basic strategies here. So one thing you'll see me do in the example is I will organize the information into a chart. That helps me make sure that I don't mix any of the values between the stages. And the only connection between one stage and the next is going to have to do with the ending velocity of one stage being used as the initial velocity for the next stage. Of course, feel free to stop the video to copy down the problem if you'd like. So there are actually 3 stages to the ball's motion in this problem. The ball first experiences an acceleration as it's being hit by the tennis racket, and then it moves, it says, with a a certain speed at that point. It's not contacting the racket anymore. We're not going to imagine there's any air resistance or anything. We're just looking at the horizontal part of the motion during this problem. So it's going to be a certain speed that it continues with, and then whatever that speed is, it's going to contact the wall, and then it's going to come back and rebound. Okay, so these are going to be our 3 stages then. We're going to have a portion in stage 1 where there is acceleration. We're going to have a portion in stage 2 where it travels for this distance at constant speed. And then stage 3 is where it rebounds. And we want to be extra careful with that to pay attention to direction. That is really messy, sorry. All right, so let's take a look at maybe organizing the information in our chart here. Give myself some room to write later. So the tennis ball is served. So before it's served, it's not going to have any forward motion until we hit it. Okay, so the initial velocity would be 0, and the acceleration is 160 meters per second. So we'll consider that our positive direction. And it says that it's in contact as with the racket as the ball moves for a distance of 1.8 meters. Okay, so taking a look at that information, I'm eventually going to want to know how long it takes the ball to reach the wall from this moment when it's first hit until it again first contacts the wall. So I'm going to need to know time, and then I'm also going to need to know the velocity. It doesn't ask me to find that velocity, but the ending velocity here becomes my initial or really constant velocity for this next section. So let's go ahead and do that first. If I use v squared equals v sub o squared plus 2 alpha delta x, initial velocity is 0, so that would be 2 times 160 times 1.8. And so this velocity that I find here, after I square root, I find that that's 24. Okay, so that's going to become my constant speed, my initial speed that stays constant for this part of the motion, the second part of the motion. What else I know here is, or what I can find, is the time. So delta x is equal to v sub o t plus 1/2 at squared, but since v sub o is 0, I'll just write down 1/2 at squared. So that's 1/2 times my acceleration. My time is my variable, and the distance traveled is 1.8. So if I solve this for my time, I find that t is 0.15 seconds. 5 seconds. All right, now, again, the only number that I can transfer over is this velocity. The amount of time it was in contact with the racket means really absolutely nothing to the second part of the motion. It doesn't know how long it was in contact. So in the second part, I am going to need to know that time so I can answer part A. So I can say that the distance traveled at a constant speed is just velocity times time. So that would be 24 times my 0.15, I'm sorry, 24 times, I'm sorry, I'm messing this up here. I just did exactly what I said not to do. I don't know the time. What I do know is that it travels 14.4 seconds. All right, so 14.4 is equal to 24t. And so I can solve for my time. This is 0.6 seconds. So now I actually can answer the first part of the question, because these are the 2 times that I would add together to say how long it takes the ball to reach the wall from when it first contacts the racket, so before it's accelerated, to when it hits the wall. So that total is 0.75. All right, and then it rebounds, which means that it's initially maybe going to the right, and then it's going to the left. So I need to make sure I pay attention to that. This 18 meters per second needs to be stated as the opposite direction to the original 24 meters per second. Remember, this number here, this 24, will become the initial velocity for this part. And reading from the information, the final velocity, I'm going to record as a negative number to indicate that it changed directions. And it took a time of 30 milliseconds to do this. A millisecond, just like a millimeter, is 1,000th of something. So there are 1,000 milliseconds in 1 second. So 0.03 seconds. And so if I want to find the acceleration, which was my second question here, acceleration is my change in velocity over time. Again, pay attention to direction here. So the final velocity is -18, and the initial velocity is a +24, and then I divide by my time interval, which is 0.03 seconds. This gives me actually a negative number, which, you know, makes sense. This object was traveling to the right, and then later it's traveling to the left, and so something had to slow it down and then speed it up again in the opposite direction. So all of that points to a force that points to the left, which would be an acceleration value that's to the left. So this negative sign doesn't mean slowing down necessarily. It just means that it points towards the left-hand side, which means it could be increasing the speed or it could be decreasing the speed, depending on which value the velocity points. But my final answer I should just state as a positive because the question asked for magnitude. So my magnitude of A is equal to 1,400 meters per second squared.